Hello, hello, my calculus people. Today we're going to be looking at the definite integral. This is our second day in the definite integral. So let's get started. Have your TI-84 calculator. We're going to use that to calculate some integrals, and we should be set to go. So let's go ahead and get this done on the next screen. So we have a Gallimimus flock stampeding. The flocks are running from a Tyrannosaurus rex set free from its enclosure. This gives the scientists a perfect excuse to study the speeds of Gallimimus G528RS and G805KS. The two dinosaurs run with very different velocity curves, so can we use calculus to predict their travel distances? So, part 1. We'll call this, we'll call it what it is. G58RS is running with a velocity curve that is linear. Let's say that this velocity curve is 37 plus 16 thirds t minus 6 feet per second. Part A, graph the curve for G528RS. Now I know it's probably been a while since you've graphed lines here, but this really isn't that bad. It looks like a mess, but it's not that bad. Already you can see that it's in point slope form. So when t equals 6, this bit over here is 0. So the velocity, we'll call it VR, that is going to be 37. So that's one point that you can go ahead and plot, 6 and 37. We're right around there. And then the next point that you can plot, well, everyone's favorite is going to be at t equals 0. So the velocity r at 0 is going to be equal to, well, let's see. If I substitute a 0, of course, this becomes a negative 2. A negative 6. Negative 6 divided by 3. Negative 2. Negative 2 times 16 is 32. Negative 32. 37 minus 32, that's 5. So, again, this isn't a calculus review or a algebra review, but I thought we would graph the line anyways. That should just about do it for part A. We have graphed the velocity curve. So we can estimate the velocity at any point along this curve just by figuring out what the y-coordinate is. Part B. Write and evaluate an integral to compute the distance that G528RS runs after 3 seconds, 6 seconds. So we'll get our integral then. The integral is area. So the distance is equal to this integral, or this area, which would be between the x-axis and the curve of VR, and between x equals 0 and x equals 3. 3 is 1, 2, 3, right over here. So let's figure out this area. What do we have? This is a trapezoid. This base over here on the left side is, what is that? T equals 5. And on the right side, right over here, that's going to be V of 3. Let's calculate V3. So 3 minus 6, of course, is negative 3, which negative 3 divided by 3 is negative 1. 16 times negative 1 is negative 16. And 37 plus negative 16 is what, 21? 21. So over here, that's 21. I'll leave this. This is 3 and 21. This is 0 and 5. And then the height here, well, the distance between these two is 3 units. All of that gives us a distance of 39 feet. Next, let's take a look at the area from 0 to 6 seconds. Similar integral. It's just the upper limit is now 6. So now our area goes all the way from t equals 0 to t equals 6. We already calculated that y coordinate. It was 37. So now the area for our, that tells us the distance, is going to be the area of this larger trapezoid. So what is the area of this trapezoid? Again, 1/2. The base on the left is 5. The base on the right side is 37. The height this time is 6. And this is equal to 126 feet. Okay, and part C, write an integral expression for RT, the distance that G528RS runs after t seconds. And if you notice the pattern here, the only thing that's changing is this upper number, this upper limit of the integral. When we write the integral this time, the upper limit is going to be replaced with a t. Okay. Now if I want to find at 6 seconds, I meant 7 seconds, we just need to replace the t with a 7, and we're going to evaluate this. So we already know it's going to be a trapezoid. 7 seconds is right here. Let me just replace all of this now. Oops. Okay. On the right side, if we substitute 7 into our formula for VR, we get 42.333. Left side is still 5. The right side is 42.333. And this time we have a base of 7. So when you calculate that, you will get 165 2/3 feet, 0.666 if you like. So that should give us an idea about how this function is kind of extendable. Really, we've made a function using an area formula that will give us the distance that this particular Gallimimus ran. So keeping this in mind, this right here, this is it's a function for distance that is defined by an integral, or an integral function for distance, which is something we haven't seen before. It's kind of new. Okay, so this is how you do it with calculator. You get these areas using exact geometric formulas. But now let's take a look at the next Gallimimus, which is G805KS. Okay, this is a quadratic velocity curve, and I'm not going to labor graphing the quadratic. I'm just going to go ahead and put it out there. Now, with the last section, we were able to, let me back up a little bit. Next is to write and evaluate integrals to compute the distance after 3 seconds and 6 seconds. And we'll put both of those integrals there because now that we've seen them, there shouldn't be any mystery to what they look like. So there are the two integrals. We got this one over here from 0 to 3. And we got the one on the right that has the limits going from 0 to 6. Let's do the 0 to 3 one first. 0 to 3 gives me an area that looks like this. So to be clear, that yellow area is the same distance, or evaluates to the same distance that Gallimimus G805KS ran. Now, how do I find that area? Well, we're going to go ahead and use our calculator like this problem suggests. So we're going to use a calculator to do that. Let's pull out our TI-84. Okay. And I've got a few tips for you on using the TI-84. And the first one is to take your function and put it into the y equals menu. So I just clicked y equals. I'm going to push clear to clear that out. And I'm going to type in there the formula for the distance that G805KS runs. Now your calculator may or may not have the pretty print function. I'm finding more and more calculators are having them now. So you can get that 11/12, but anything you do, just make sure you get that absolutely correct. And from here, we're going to go to the home screen. Now in the home screen, you can actually calculate an integral using your calculator. And I'll show you two different ways of accessing the same function. The first way, and this is the old school way, is to push the math button, which is located just below alpha, and take a look at number 9 that says FNINT. We're going to click number 9, and look at that. It just sets up the integral for you. I'll clear that off to show you the other way to get this. This is the new way of doing it. You would push alpha and then trace, and that brings up a soft menu with all of the y1 through y0. Again, this is the first one, so I'm going to push y1. Oh no, I did the wrong one. I'm sorry. It's alpha and window. Alpha window gives you FNINT as option 4. So you can do what I did, scroll down to it and push enter, or you can just press the number 4. In both methods, you get this blank integral, it's template of an integral, and you just need to fill in all of the dotted boxes. So we're going from 0 to 3, and we want to put y1 in there because if you remember, we typed our function into y1. This is where we do alpha trace y1 and dx. Now, one special note about this. Notice that even though this function has a t in it, on my TI-84, I have to type an x. There really isn't, your TI has to have an x in order to graph. And so you just get used to kind of switching back and forth between, on the paper it's a t, and on the calculator is an x. And that's probably good for your mental flexibility anyways. Back to the home screen, I'm going to push enter, and that should give me the result I'm looking for. It's 59.25 feet, I believe. Now that we have the first part done, we'll go ahead and let's see the area from 0 to 6. Let's shade that in. There's our area. And again, to make that connection, the area of the blue area under the curve is the same as the distance that's run by this Gallimimus. So then that area is the same thing as this integral expression. I'm going to go back to the calculator to calculate this, and I'll show you a shortcut if you don't want to type that entire thing over. We're going to push the up arrow until we highlight the entry that we want, and then we're going to push the enter key, and that will copy and paste that into the next line of the calculator. Click the back arrow a few times, and you can change that to a 6 and push enter. So a lot of students find that to be faster than just typing out the entire thing. I don't know, it's totally up to you. So in 6 seconds, Gallimimus G805KS runs 168 feet. Part C says to write an integral expression for KT, the distance that G805KS runs after t seconds. So KT, that's going to be an integral from 0 to t of, and I'm going to copy down that, 11 over 12 negative. Now I can't use a t here, so I'm going to switch it to an x. And the reason that I can't use a t is that if I have the t here as the upper limit of my integral, then it doesn't make sense to put it into the integral because, gosh, I don't even know how to explain what that would mean. We're graphing in terms of t, and that, no, if you think of something, let me know. But suffice it to say that the variable of integration needs to be different than any variable that appears as a limit. Okay, so that takes care of my part C, and part D is to evaluate and interpret K7. The integral here shouldn't be surprising what K7 looks like. K7 is going to be the exact same integral as KT, but we're just replacing a t with a 7. Let's grab our calculator, and really quickly, you'll see how fast this goes. We'll get our integral from a copy and paste, change that 6 to a 7, push enter, and we get 206.694. So from t equals 0 to t equals 7, G805KS ran a total of 206.694 feet. Now that's not an approximation anymore. That's the exact value. Or that's the exact value if that curve is correct. So area is the same thing as an integral, and we can calculate that integral using our calculator, or we can calculate that integral using geometric methods. Okay, this is what I was talking about earlier. Notice how this is incorrect, how t and t match here, but this is t also. That's not correct. You cannot put t as the variable of integration if it's a variable of a limit variable. So this one is correct. Make adjustments to your work if necessary. Yeah, we did that already. So that brings us to our important ideas, and I'll summarize them quickly for you. The integral is a calculus way of writing the area. It is an area function. So when I write the integral from x equals a to x equals b of f of x dx, that's going to give me the area between the curve of f of x and the x-axis, and between x equals a and x equals b. So there are a few ways now that we have to calculate this. So number one, we can use exact geometric formulas. And number two, we can use the FNINT function on our TI-84 calculator. So those are the two ways that we have of exactly calculating the FNINT. Now, don't forget, from the first section, we saw that you can estimate that integral also by using rectangular approximation methods, or you can estimate that just using any area formula that you have handy. Okay. If you're just asked to find an area or find an integral, just use any area formula you have. It doesn't have to be a rectangular method, although the rectangular method will play big into the next couple of lessons. So that is our integral. Let's see how we're doing here. Yeah, I think we're going to go ahead and do the check your understanding today. So the first part is we have this gallimimus running with this curve. And how fast is this running after 3 seconds? Write an integral expression and then evaluate that function a few times to create an approximation for the graph of mt. Okay, so first of all, I'm noticing that we're not plotting the graph of Vm, we're plotting mt. So let's figure out how fast G1030MF is running after 3 seconds. After 3 seconds, how fast, that's going to be the velocity. So Vm at 3, that's going to be equal to -2/3 t minus, no, not t, but 3 minus 6 squared plus 34. Grab your calculator and hit calculate. So I'm getting Vm equals 28 feet per second. Part B. Write the integral expression for mt, the distance that G1030MF runs after 10 seconds. 10 seconds. So this is going to be the integral from 0 to t of Vm, change that to an x, dx. Now, something that I didn't mention earlier, and I'm sure I've mentioned it in other sessions, but if they give you what Vm is equal to, then you're free to use Vm in your work. You don't have to write out the entire thing. So there's my integral expression. I'm going to go ahead and put this in the calculator because I'm taking a look at, we're going to have to evaluate m at a few places. So we want m0, we want m1, we want m2, we want m3, and we want m4. So let's evaluate those. Okay, there's Vm in my Y1. Back to the home screen. And wait, what just happened there? I think I messed up. Definitely there was a slip up there. I don't know what happened. But here's my Y equals. Quit to the home screen. And we're going to integrate again. So I'll remind you that is going to be from the alpha window and number 4. And we're going to integrate from 0 to 0. That's the first one. Y1 dx. And that should give me 0. And I hope that makes sense to you, because if we're going from 0 to 0, there is literally no area to accumulate. So without even using the calculator, we should have known that this is equal to 0. So let's get back to the work. And actually what I'm going to do is I'm going to be a little bit more thorough with what I'm doing here. So I'm going to say that m0 is the integral from 0 to 0 of Vmt dt, and that's equal to 0. Again, that's because there is no area between t equals 0 and t equals 0. Let's do m1. m1 is going to be the integral from 0 to 1 of Vmt dt. On our calculator, we're going to recall the last function, change that upper limit to a 1, push enter, and I'm getting 13.777. So that's 13.777. That's good enough for me. 13.777. 0, 0, 1, and 13.777. 10, 20, 30, 40. Yeah. Right there. Okay. T equals 2. This is going to be the integral from 0 to 2 of vmt dt. Let's see what that is on our calculator. Call up that last function, change this to a 2, and I'm getting 34.222. See, a T. Oh, I think I messed up here. Was that 13.7? T equals 2, I'm getting a 34. 10, 20, 34. It's kind of like that. Okay, how about at t equals 3? M3 is going to be the integral from 0 to 3 of Vm dt. Let's figure out what that is. Hopefully the redundancy is kind of setting in. We're seeing the same thing over and over again. T equals 3. I'm getting a 60. T equals 3. I'm getting 60. T equals 4. That's going to be the integral from 0 to 4 of Vmt dt. And to the calculator, change that to a 4, and I'll be glad to be finished here. That's going to be 89.777. 89.777, which is pretty much 90. So here is our distance curve. Hopefully you see that there is a curve to it. It's not a straight line exactly. So the distance that, what's this one, G1030 MF is running is, well, it looks like we're picking up speed. So that's it for us today, and hopefully we've got some new calculator skills and a little deeper understanding of how an integral is related to area. And I'll see you next time, calculus people. Oh yeah, my nephew keeps telling me that I need to say things like subscribe, press the subscribe button, and ring the bell, whatever the hell that means. So subscribe, hit the bell. I'll see you guys later. Oh, I guess you can like the video too, right? Push the like button. What the hell? Who's it gonna hurt? I'll see you next time.